Hello, we have 4 o'clock. I think we can start, 4 o'clock my time. Just a quick check, Ismail, can you hear me, see the screen?
I can hear you, see your screen and everything. Hello, everyone.
Perfect.
We're glad to welcome you to our RFEM and RCEP as a software. So yeah, today we're going to be talking about the finite element method. We're going to be making a lot of examples together during these couple of hours, and I hope you guys enjoy it and have fun with it. Good luck,
Thanks.
Björn.
Thanks,
And
Ismail.
yeah, I'll be there to answer your questions via chat. So do not hesitate to ask any questions. I'll be there for you.
Yeah, that would be nice to have a bit of back and forth, so please don't hesitate to ask questions. And just further on to what Ismail was saying about the community that we're creating at Bluebell, I think it's really nice to bridge the gap between what one learns at varsity and what one is expected to do in the field in the practice. So that's what we hope to do a little bit today, is to break down the walls between the theory that we're learning at university and what one is expected to do when modeling, when doing something in a design office. Just going back to some of the admin things for today, you'll see that you have a pop-up for the webinar, for GoToWebinar. You can raise your hand if you want to bring our attention to something, asking questions. As Ismail said, he's sitting there and he'll be happy to answer your questions. We'll also be providing some polls during the course of the presentation. Just after the presentation, or if you get lost during the presentation, that is no issue, because the whole webinar has been or is being recorded, and we will post that on our website as well as on YouTube afterwards, as well as getting a certificate from the training along with attachments of all the models that I will create during this presentation. I will also switch off my camera so that we can get a full just a full look of my screen for the entire time. So this is, we offer a plethora of webinars and training series for everyone. We are in our 3rd training series, and that is the Introduction to FEM, Finite Element Method, Finite Element Modeling, or Finite Element Analysis. There are many different explanations for the acronym. We've already had Introduction to Member Design and Strength and Materials, and then interesting topics coming up: steel design, concrete design, and timber design. Diving into a bit more detail of what we're going to be having a look at today. The basic principles of finite element analysis, just like I said, bridging the gap between the heavy technical things that we learn at university and just basically summarizing it up and making it more understandable and putting into practical applications for what one has to consider when modeling in RFEM. Then we will look at our first introductory example, which we can model together, and that is a continuous slab. We will be looking at different ways of modeling the slab and comparing what the results that we get with what we expect to get from our basic principles of beam theory. Mentioning beam theory, we're also going to have a look at plate theory. We'll then have a look at a couple of already predefined models, looking into nonlinear calculations, which won't require much following along. And then afterwards, we'll end up with having a look at some singularities where everyone will be able to model along again. So before we get into the basics of finite element analysis, we've introduced ourselves, so it might be quite nice just to know a little bit more about where you guys come from. So I'm just going to start a poll, and you should see it now. I'll just wait a bit until everyone has answered. Okay, that looks good. So it looks like quite distributed between masters and bachelors. And then the second question is, I'll start it now. Have you already had a course in FEM? Just a yes or no. Okay, so the most say yes. I'll maybe be able to skip over the basics of FEA a bit quicker. As you may know, that computer programs are normally based on the displacement method. That's the inverse to the force method. And that basically means that the computer solves for the unknown, and the unknown is the displacement method. Is the displacements or the deformations on the structure. Getting the internal forces, the stresses, support reactions, etc., is then done by post-processing once we have the displacement vector result. Analytical solutions of structures are very hard to do in reality. Sure, if we have a simply supported beam, we have the theory and the principles to be able to do that. But when we look at large scale structures, when we start modeling plates, that becomes very hard. And that's where our FEM comes into play. And we will then have a look at
Bjorn?
Yeah.
I'm sorry to interrupt you, but it looks like we're still on the poll, the question. I don't know if you're showing something because we're
Thank you.
looking at the poll.
Sure.
Yeah, now we see the results.
And then let me take that away.
And now we don't see a screen.
Okay. Let me just start the screen recording again.
Yeah, there you go. We have it now. Oh, we had it for a second, and then now we have your. Yeah, now we see it. There you go.
All good?
Yeah, basics of FEA, right?
There we go. Thanks for that, Ismail. So yeah, like I said,
just put it on full screen, and that would be. That's a lot better. Yeah.
Perfect. Thanks for that. So yeah, like I mentioned, we are based off the displacement method, which means we are solving for the unknown displacements, the deformations on the structure. From then to get the forces, it's a post-processing result. So that's how we get our stresses, our internal forces, etc. Our basic principles from what we learn at university, being analytical solutions, is quite hard when we extrapolate that onto bigger structures. And that's where we go into numerical solutions. And that's where the finite element analysis comes into play. And what we do is we take this real structure, a continuum, and we break it up into a mesh of finite elements. That's where the name comes from. And each of these elements are connected with one another. And it's that interconnection which is quite important, because when we come to assembling everything again, which is on the next slide, that's how we describe the structure as a whole and not just these individual pieces. The nodes is something that's very important. All of our results, everything that we do is concentrated at the nodes, and then broadcasting that onto our whole problem is done through interpolation. Mechanical behavior is described by approximation sets, and a very important part of the whole process is discretization. And that's when we take the problem and we break it up into smaller pieces, and we can describe that behavior of the smaller pieces quite accurately. Just to explain that or show it again or graphically, we start off with the structure as a whole, the problem as a whole, which might be quite challenging to describe just from the look of it. So then we cast a mesh over the entire structure, and each mesh is the standard element, and we know the behavior of those elements. Then we transform the stiffness relations of each single element into the global picture, and that's how we can describe the whole structure. And that's part of the assembly. The next step, which is very important, and that's quite often what happens when we have an error when running an analysis model, is just getting the consideration of supports correctly. Is our structure stable? Have we provided enough supports for the determination of the displacement vector to take place, which is then what we call the solution of the equation system. And then as engineers, we want to work with bending moments, we want to work with axial forces and stresses. And in order to get there, it's part of the post-processing where we get to determination of these forces, which is very useful for when we come to designing. That then brings us to our first example, which is going to be a continuous beam or a continuous plate. It's a two-span beam or a two-span plate. And it's always better to learn through doing. So what we want to do in this example is cover the topic of our finite element mesh, the implications that the mesh size has on the convergence behavior of our results. So in this case, we're going to be looking quite in detail at the hogging moments over the internal support. In order to validate our results, we're also going to be having a look at what we expect, and we'll simplify it down to a single beam, two-span beam, and we'll have a look at how the different mesh sizes correlate and how that converges to what we deem to be the appropriate solution. A few other things that we'll look at in RFM is just how we can look at the distribution of internal forces. We'll then touch on the subject of shear stiffness and the consideration of shear stiffness when running analyses in RFM6. And then we can also look at result smoothing when it comes to interpreting the results a bit better. So I'm going to switch to RFM now. Ismail, can you see the change on your side?
Yep, all clear.
Cool. So we're going to start off by creating a new model. I'm not going to run through all the different user interface aspects of RFM. We have quite a few training tutorials which will help you, so I'll skim over that. But if it is too quick or if it is too slow, you're welcome to mention something in the chat so we can adjust accordingly. So the first example that we're going to look at is this continuous plate. So all models need to be given a name. And then another important thing to mention is just the type of model. Here we can see a very useful image on the right, and as we toggle through the different options, we can see certain portions of this example model being grayed out, as well as different axes having different colors, some being grayed out. And that's basically showing that the different degrees of freedom which are activated for our various scenarios. So for the plate, we want to consider bending in both the X and the Y axis, and we will have deflections in the Z axis. So we're happy with this 2D XY plate. So I click on OK, and that will then generate a new model. Just in terms of, since this is an international webinar, when it comes to language settings, we can go under options, program options, and under settings, you can have your language of choice. Also, when it comes to appearances, under display properties, you can toggle to a dark background if you'd like, but I prefer sticking to the white background. But again, it's just a matter of personal preference. So much for that. So let's start off with modeling. What we want to define, and going back to the presentation, is we want to define 4 surfaces. So we'll start off by just creating one surface and then copy them across. So to do that quite simply, we can go up to new rectangular surface. And since we are in the structural engineering domain, we don't just look at geometry. Geometry has meaning to us, which means geometry has a depth, and that depth, that thickness, is assigned a material. And that's exactly what we want to do here. So for this example, we're going to have a thickness of, let's say, 300 millimeters. So we will create a new thickness. And like I said, each thickness has a material, so we can go into the material library. And as you can see, there's quite a few materials to choose from, which might be a bit overwhelming. One can also search, which makes things a bit easier. So I want to go for a concrete material, just normal grade concrete, not lightweight concrete, and double click on C3037. And that's, now I have my material defined, and the thickness, as I mentioned, I would like 300 millimeters as my thickness. So I click OK. And then here we can see the summary. It's a thickness of 300 with a material of C3037. Just another thing for what we are wanting to do with this example is we want to just switch off the lateral strain effects. Explanation to that will come a bit later, and that we can find under our material properties. So under material properties, we can see the standard Poisson's ratio for concrete, which is defined at 0.2. It's grayed out and we can't change that, but in order to change that, I just click on user defined material and I'll set that value now to 0. I click on OK and OK again. And now we can model our plate elements. To make it a bit easier, because this is now in the 3D plane, I'll just change my view plane to look in the XY plane. And we will have dimensions of, I think, a 10 by 4 plate. So start at the origin, go across 10 meters and down 4 meters, which is there. To exit the modeling mode, I can either right click or hit escape. And there we have defined our first plate. As I mentioned, this is going to be a 2-span plate. So we want to create a line support in the middle of this surface. So for that, I need to draw a line, and I can draw that in the middle, and it snaps quite nicely or quite effortlessly to the middle of the surface. One thing to maybe mention here is the different node colors. If you see that we have red at the corners and blue for this line that we just created. So if I double click on that node and I go to main, it has a different node type, and this node type is online. And this is maybe coming back to the concept of FEM. It's all about breaking up a big model and then making sure that we have the interconnectivity correct. And this is quite a nice thing about RFEM, is that the interconnectivity, it's very intuitive and it's quite clever in the way it does it. And just to illustrate that further, if I now click on the line, it has a new tab called Nodes Online. So it recognizes that node from the line that I just created, it belongs to it. So everything is nice and connected. The red nodes is just a standard node type. So there are different node types. So that's what the different colors mean. We will now go on to supporting our structure. Obviously, no structure is complete without supports. So we'll start off on the left edge. And basically what we want is, like we know from our structural analysis lectures, we'll have a pin support here and then 2 roller supports on the interior support and on the far right. So there are lots of ways in RFEM to assign attributes. It can either be on this left navigation bar, it can be using these quick icons at the top, or by clicking on a line and right clicking for more options. We'll start off with this option, assign line support, and a hinge support is what we want. So we want to assign that now to a line number. So we'll click on line number 1, click OK. Okay, and now we've assigned a line support to that first line. These 2 lines, we will have a roller support. So again, it's now realized that I've clicked on lines 3 and 5, and the line support type. The only 2 options we have here is hinged and rigid, and that's not what we want. So we want to look at having a new line support. So I go create new line support. And there are some presets at the bottom. I can either define things manually, or I can use the preset, which is sliding an X, and it knows what to do. So I click OK, and OK again, and then now we have our supports. Next thing that we want to do is assign a surface load to our plate. All loads belong to a load case, and we see our load cases at the top here. For this example, we just want to control one attribute, and that's the surface load that we apply. So I'm going to deactivate the self-weight for this example, and that's easily done just with that checkbox. I'll click OK. And now when it comes to assigning a surface load, you can just say new surface load, and we'll make it a magnitude of 10 kilonewtons per square meter. We want to assign it to our surface, which is that surface number 1. and we click OK. And OK again, and then there we see our surface load. We can also adjust certain settings. If we don't like the size of it, you can right click on the load, make it smaller, bigger, depending on how you'd like to view the model. For surfaces, an important consideration, as mentioned, and what the aim of this example is to look at the different mesh sizes and the influence that mesh size has on our results. If we didn't do anything with the mesh sizes, then the elements would take over a default mesh size, and we can see that by going under Calculate and under Mesh Settings. And this is, in general, what will be applied to a surface if we don't tell RFM what to do. We want to be a bit fancier in our example, and we will then assign different mesh sizes for the different models for the different plates that we create. So one way of doing that is under Types for Surfaces, Surface Mesh Refinements. We can right click and say New Surface Mesh Refinement. And we will have in the PowerPoint, which just showed we had 4 different surfaces. So I will create 4 copies and assign different mesh sizes of 2 meters, 1 meter, or 1.6, 0.5, I think would be good, and 0.1. So we have our 4 different mesh sizes. Click OK. And here we can see the 4 different mesh sizes I just created. They are shown in blue, which means that they haven't been assigned to a surface yet. And we'll get to the assignment later on. Obviously, we need to create a copy of this plate before we can assign it to different surfaces. So that is quite easy to do. I just select everything. I go right click, copy, and we want to create 3 copies so that we have 4 in total, and that length is 10 meters. So I'll make a displacement vector of x is equal to 11 meters. So we have 1 meter between each model. I click on OK, and then there we can see our 4 different surfaces. You'll also notice that it's now going out of the default grid plane. We can change that quite neatly by right-clicking on the canvas and going work plane, grid or snap, and we can make it dynamically adjust according to the size of our model. Right, so we've created the copy, and now we want to also have a beam element for us to justify or quantify our results and to further analyze the convergence behavior. In order to do that, similar to how we created a new surface, we create a new beam member. So yeah, we don't need to change anything here. We just want to assign the section. The standard or the default is a steel section, and that's not what we will use for this example. We want to create a concrete member which resembles a meter strip of what we're doing with the surfaces. So under the import section library, under the massive tab, we can just get a standard rectangle. The breadth, as I mentioned, we want to look at a meter width. So we assign the breadth of 1 meter, and the depth of our slab needs to be the same as the depth of the beam that we are modeling. So we'll make that 300 as well. Then the material should also be the same as what we're using for our surfaces. So we'll assign the C3037. And I think that is all. Yeah, so now we're ready to draw the beam. We can snap it to the middle, and the length should be 10 meters. And we can just do that by typing in 10, and you'll see on the member length dialog that adjusts accordingly. So there we have our reference beam element. We can now look at the mesh assignments. It's a bit hard to see the meshes if we have the loads on, so we can deactivate the loads just by toggling off the show loads. Then going back into our mesh refinements, if I double click there, we can actually start giving it some values for the first mesh size is not assigned to a surface, and we want to assign that to our first surface. Click OK and click apply. Same for our second surface. And apply. And for our third as well. And we do the same for our last surface. So we don't see anything yet, which might be a little bit confusing. In order to see the different meshes, I mean, that is part of the calculation step of RFM. So we can do that beforehand, and we can say generate mesh. And here we can see our different meshes. So on the left, we have that mesh size of 2 meters, and that is very coarse. And then we have 1 meter, which looks a bit better, or was it 1.6, I think it was. Then 0.5, that's looking quite nice. And then we have a very fine mesh of 0.1. We can see that. And then the final thing that we want to do is now we need to support our beam because this model will not run, as you know, as engineers, we need to add supports to make the model meaningful. So we will need nodal supports in this case. So I click on the node and I make it the similar or the same conditions as what I'm giving for the plate. So we have a hinged support on the left. We need to now create a node in the middle, similarly to how we created a line for the surfaces. So in order to do that, I can right click on the member. And the members, I can say divide member by a number of intermediate nodes. We only want one intermediate node, and let's create the node without actually dividing the member. So I click on OK. And then there we have our intermediate node, and it'll have the same support conditions as the end node. So let me just select those and assign nodal support. And we want a roller in the X direction. Let's just have a look at how that is defined. Yeah, looks good. I click on OK and OK again. And then there we have our reference beam member. What we'd also like is to apply the same loading that we have on our beam member as we have on our surfaces. So in order to do that, I go to assign member load or new member load, and we give it a magnitude of 10 kilonewtons per meter. We click on assign to members and we put that on that member. Click OK, OK again, and then there we have our member. Just going back to these support conditions, maybe it's just coming out of experience, but we would like to also make sure that the member is not free to rotate about its own axis. So we just make sure that the rotational restraint by X, so the rotation about its own axis, is restrained. Click on OK, and then there we have it. I think that is enough now to run some calculations. So under calculate, I go to calculate all. Let's see. Before we go into the results, Ismail, do we have any unopened questions, or how's the pace for everyone?
So far, so good, Björn. All questions are being taken care of. I just wanted to name a few things, just so our audience can have a pretty good idea about what RFIM, how RFIM is different from the other competitors in the field of building information modeling. In this context, you were showing the surfaces, and just in case one of you did not take part of the other online trainings where we talk about the different features in RFIM. I just wanted you to show them how to render the surfaces as actual surfaces with their thickness, because it's all possible under the visibility navigator. What is it called again, Bjorn? The viewing, right, display navigator, and you can choose whether you want to see the surfaces including thickness or including lines and everything. It's a little bit down on your way down when you rendering. There you go, rendering model, right under that one. You got rendering model, surfaces, solid model. Under solid model, you find surfaces, and you can choose whether you want to render it in a way that shows their thickness or not. So just if you wondered why we are looking at surfaces that look like actual two-dimensional surfaces, no, they're not. It's just the way we render them, and that's one thing you can change whenever you want on RFIM. One more thing you mentioned, you talked about nodal supports. It brought to my mind the fact that we have videos about what nodal supports are and how you model them on RFIM. You can check that out on our YouTube channel under the Structure Analysis Wiki playlist. We take, that's actually how the Structure Analysis Wiki works. We take one terminology in RFIM and we explain it and show how a user can use it in an efficient way. And the last thing that I wanted to mention is seeing how user-friendly our interface is. I wanted to let you know that we have another YouTube playlist called Product Features, in which you can find the different special features of RFIM 6 that make us one of the top softwares in not only in Germany but also in the entire world when it comes to features that make a civil engineer's life a lot easier. That would be it.
Thanks, Ismail. Yeah, thanks for that. We'll get to the YouTube and the website later towards the end. There really is so much information, obviously meant in a positive way. I mean, you guys won't need Netflix or Amazon Prime.
Absolutely.
So we'll jump to the YouTube videos. There's a lot that can help you, and we love the interaction as well. So as mentioned, those answers to those types of questions, the wiki, the structure wiki, that all comes from interaction with students and with clients. So it's something that we do appreciate, and I can only Ismail, I can only
and it's something that we take pride in, because we are proud to be one of the few, actually, if not the only structure analysis software to provide this kind of content on YouTube, Instagram, LinkedIn, and all social media. So we would love it if you take advantage of what we are providing in terms of YouTube videos and tutorials.
100%. Yep, I agree. Let's go back to our example. So just to recap what we're wanting to look at, we want to look at the convergence behavior, or the effect that different mesh sizes have on our results. Specifically, what we are going to look at is bending moments. So default after running a calculation is our global deformation, which is the absolute value of U. It's the square root of the sum of the squares. So your X deflection squared plus your Y deflection squared plus your Z, etc. I'm not going to run through all the degrees of freedom. So let's change the view of that and maybe just explain the different subscripts, because for surfaces and beams it is a little bit different, and it's obviously very important that you are looking at the correct bending moment, otherwise you'll be designing for the wrong, or in the wrong direction. Surfaces and beams are a little bit different. So let's start off with our beam example. We can go under members, internal forces, and we will want to look at our MY bending moment. What does that mean? My means our bending moment about the local y-axis. So we can right click on the member and say local axis systems on, and we can see that green is for y, and that's pointing that way. Sorry, the support is hiding it a little bit at the moment, but it means that we have the bending moment about the y-axis. It's just a coincidence that that's the same as the global axis right now, but if I had drawn the member perpendicular to this, then the local axis would be pointing in the same direction as the x. So always important to look at the local member axis when interpreting the results. Obviously, this is quite a simple example, so we know that my makes sense. For surfaces, it's a little bit different. For surfaces, it is not a bending about a axis, but it's along the axis. So for surfaces, we want to look at our internal forces. Now, the contour plot it might be a little bit hard to interpret. A very neat way to look at the results a bit better is with a result section. So we can draw a result section quite easily by 2 clicks. So we'll take it from the middle of the surface and draw it right across to the middle of the other end. And we click OK. And now we have the results that we can compare quite nicely with our beam example. And I want to switch on local extremes, so it gives me all of the results. And here we can see a bit of a different behavior for the different members, for the different surfaces with different mesh sizes. Just going back to what we are wanting to expect, we wanted to expect something along these lines, 31.18, and we see with the coarse mesh, we start off at 26.38. Maybe I'll just switch on the mesh sizes again and the loads. There we go. We see for coarse mesh, we have probably underestimating it, and as the finer the mesh goes, the closer we get to reality of the 31.18. The take-home message that we have here is you want your mesh to be as fine as necessary, but as rough as possible. If you have a very fine mesh, that has an influence on the computational time needed by RFM6. So again, we want it as fine as necessary, but we don't want it too fine. It must stay as rough as possible so that we have that trade-off between computational efficiency and realistic results. Again, so finer mesh doesn't always lead to more accurate results. We also want to place our finite element nodes strategically, so at points of extreme values or at design points. Looking more in depth at our beam, if we were to look at this purely theoretically from university notebooks or Schneider Bautabellen, for example, which helps us with structural analysis and design, we would expect for a equidistant 2-span member with a uniformly distributed load, we have the formula of, is it negative 0.125 times the distributed load times the span squared, and that's what we expect to be our hogging moment over the support. If we do that, there is an expected hogging moment of 31.25 kilonewton meters, and we're not exactly getting that. And this is quite nice to almost understand the program and to apply what we've learned, our theory, into what we expect to get. And there isn't some black box or dark magic. There's always an explanation for how the program does what it does. And the key word here is shear stiffness. We are taking into account shear stiffness as a default for a beam member, which means the results are slightly different. We'll get an increase, and we'll get to that later in the slides. We have an increased deflection of this member, and that influences our internal forces as well. So just to show you how we can get what one would expect from calculation values, what we get from first principles is based on a Bernoulli beam, which doesn't take into account shear stiffness or shear deformation. So we can simulate that by going onto our section and edit section at member start. And here quite neatly we have an option to deactivate shear stiffness. So if I click on that and I click on OK, Obviously, we need to run the results again. We click on OK. And so let me just make sure that self-weight is off. And just to make it run a bit quicker, I'll take off our design situations. And I'll say OK. And calculate all. We should expect a different value for our hogging moment now over the beam. And there we get the 31.25. So if we take 0.125 multiplied by our distributed load of 10 multiplied by 5 squared, we get 31.25. And that's exactly what we see now for our beam after we've changed the settings of the member to not take into account shear stiffness. Just jumping back to our presentation now. We've now run through this example. We have an understanding or a feel for how different mesh sizes affect the convergence behavior. We looked at the comparison between the beam and the surface elements, and we mentioned the shear stiffnesses. Before we go into the plate theories and the different types of plate theories, we mentioned this with the Bernoulli beam. We have two types of beam theories or beam elements. We have the Bernoulli beam and the Timoshenko beam. I think we are very much comfortable with the Bernoulli beam. As we've all heard many times before, plane sections remain plane and the directors remain perpendicular to the member axis or the central axis. Because of that, we have no consideration of the shear deformations. There's a rigid shear stiffness. On the other hand, the Timoshenko beam, otherwise known as the deep beam, we say the cross section remains plane. There's no distortion in that regard, but the directors, those do not remain perpendicular to the member axis, and we get this additional rotation, what is known as shear deformation. So here we have the consideration of shear deformations, and the shear stiffness is limited, which means it isn't rigid. A little description of that. Here we can see that these directors for the Bernoulli beam is initially perpendicular to that dotted line. With the deformation, it remains perpendicular. With the Timoshenko beam, the dotted line shows what the Bernoulli beam would do. Here we have something different, and we have this shear deformation. That is then transferred to our beam theory, our plate theory. Plate theory was a further evolution of what we did or not we, but what was done for beam theory. And the Kirchhoff plate is analogous to our Bernoulli beam. So we take on a certain number of assumptions: geometrically linear elastic material, cross sections remain flat, and we have no consideration of shear deformations. The Reisner-Mindlin plate theory is equivalent to our Timoshenko, which is our deep beam. And here we say that we have a consideration, or not we say, we have a consideration of the shear deformation. Where do we see what happens in RFM? So jumping back to RFM, if I go on my data navigator on the left, it is part of our static analysis settings under geometrically linear. I go under edit. And under basic settings, I see that we have the plate bending theory of Reisner-Mindlin, which is equivalent to our Timoshenko beam theory. I think that is enough before we have a short little break. But before we go into the break, I thought I would start a quick poll. So just two questions. And this goes back to what we discussed about finite element analysis and finite element mesh. So the first question is, what is meant by discretization? Only one answer is correct. Just waiting for a few others. Might close the poll. All right, everyone's making this look far too easy. So yeah, everyone got it correct. It is the decomposition into finite elements, correct. Second question, and then we'll go into the break. The finite element mesh should be as fine as necessary and as coarse as possible, or as coarse as possible, as coarse as necessary and as fine as possible, or as precise as possible and as coarse as necessary. Again, only one option is applicable. I suppose the wording is a little bit trickier on this one. I'll just close the poll. So what we're looking for is that it should be as fine as necessary and as coarse as possible. Let me close that now. I should see my screen. Yep. Sorry, let me go. I think we can go into a short 10-minute coffee break. Ismail, are there maybe any unanswered questions or any remarks from your side?
You're doing it great, Björn. Everything's clear so far, and questions are being taken care of. I think we can go into the break.
Awesome. So I have 10 to 5 my side. We'll be back at 5 o'clock, so in 10 minutes. So welcome back. I think we can carry on. I have 5 o'clock my side. Just a small comment. If you guys have any comments, feel free to write it in the chat. If it's too slow, if it's too quick or not clear enough, yeah, we welcome any and all feedback. We're now going into the next portion of the presentation, and as mentioned right in the beginning, we're going to look at some non-linear calculations. So this portion, I have some predefined models, so you won't be able to model along. I think just follow along by watching and seeing the different considerations, and then when we go into the singularities portion, we'll be able to model along together again. So just running into non-linear calculations. What are we talking about here? Basically, it's typically when our linear elastic behavior no longer fits to our given problem or no longer reflects the reality of the structural situation or problem that we're trying to solve. One thing, and possibly very important to note in the beginning, is that the law of superposition no longer applies when we stepping into this non-linear realm. That applies to things such as load cases. Quite often we have our separate load cases, and we then combine these load cases according to what the relevant codes prescribed with partial or load factors, and we combine, for example, self weight with 1.25 times self weight plus 1.5 times live load. Those types of things no longer apply in the non-linear world, and we need to be a bit more, it takes a bit more effort in defining these load combinations and cases. A typical scenarios where we will look at non-linear calculations is with any non-linear effects. So that could be geometrically non-linear calculations, so our second order analysis, that is getting the equilibrium on the deformed configuration, as opposed to our first order analysis, which provides equilibrium on the undeformed configuration. Looking at non-linear material behavior, we have a nice example of that, which we'll have a look at, as well as non-linear behavior for structural objects. Elements such as members, hinges, or supports. Bracing jumps to mind when we talk about non-linear behavior of members, of elements. One can say that it is a more precise analysis, but this comes with an increased calculation effort. So again, it's up to our engineering judgment if we want to step into this non-linear world. There are places where there is no question, one has to do it. And that is where we'll go into some of these examples. So I'll just close this continuous plate example, which we started with, and wait for that to close. So our first example is a frame with tension members. This is quite common in our steel structures. So if you think of a steel hall or a storage facility or something like that, this is quite common. And just as a reminder, I think you guys can just follow along and watch. Obviously, because I have these models already predefined, it will be quite hard to try and model along at the same time. So if we can imagine a building bay out of a large steel structure, this needs to have some sort of lateral restraint. And if our given conditions is just pin supports at the bottom, our lateral loads could be something like wind. Wind can act in all directions. So when we're looking purely in our YZ plane, we'll have wind acting in our negative Y as well as in our positive Y. This then, we're talking about the topics in lateral stability. So if I take away our meshes, sorry, not our meshes, our bracing, and we try and run this model, we should get an error, and we do. Some errors and warnings occur during the calculation. If we just click on a K, it will automatically jump to our errors and warnings box, and we can get a better idea of what went wrong. The stiffness matrix is singular. It's something that you will get faced with, or happened to me quite a bit, is this error warning. And the first thing that one should do, one should think about, is always having a look at your support conditions as well as is the structure stable. And in this case, because I deleted the bracing members, the structure is not stable. So how one can include bracing members is it is a type of member. And if we typically, when we talk about bracing, that could be equal angles or circular rods. We have well, I've predefined a rod here of diameter 20 millimeters. And we can draw that now. Let's not auto connect. So draw that from one node to the other. Yes. And from there to there. Ismail did mention something earlier about the efforts with Dluba and RFM and how it's becoming, it's really taking on this idea of BIM and integrating a bit more parameterization and interoperability and ease of use in the graphic user interface. And one can see that with drag and drop, which is quite cool. If I select the two members, I can click and drag and drop quite nicely. Sorry, I should have control. Drag and drop. It's obviously not working now. When cursive presenter, I can draw it manually. So we get the section for a 20 millimeter diameter rod from node to node. Not auto connect. The reason why I say not auto connect is because the intelligence of RFM, what will happen is that it'll break up this member where it intersects with this rod, and it'll add a node there, which is usually very useful. But that's not what we want in this case, because that's not what it'll be like in reality when we have two rod members. They'll run past each other. So that's why in that instance I deselected that option. So now we have our bracing members, and if I run this now, it should converge. And it does. Now, just because it converges doesn't mean that everything's good. If we now switch off our global deformations and we look at the behavior of what's happening in this bracing, our bracing rods, which you can think of a wire, that's very good in tension, but it's almost got no compressive resistance. So if we now look at our axial forces in the members, we'll see red for tension, and we'll have compression in the other rod, which is something that we don't want. And this is an example of the non-linearity, because we need to see how the structure behaves, and then the member type needs to react appropriately. So we don't want compression going into our bracing members, and there's a couple of ways that we can do that. Just for interest sake, if I then toggle to wind in the other direction, we see we have tension in this member. If wind blows from the other direction, we now have the reverse. So we have tension in that member, which means we need to have both members in our model, but we need to define it in such a way that it is activated when it's in tension and it is deactivated when it experiences compression. And this is a type of nonlinearity which we can quite easily define. There are many different ways of defining it in RFM. So the first of which is I can select the 4 different members and double click on them. And we can say we want a nonlinearity. As soon as I click on nonlinearity, an extra tab pops up. If I go there, I have some member nonlinearity options, such as failure and compression, and that's exactly what we want. So I select that, but I can also, just to show you what other options we have, and this is the nice thing with RFM, there's a lot of different presets. I mean, I won't go through all of them, but failure in compression, or if compression fits our scenario perfectly. So we click on OK. Obviously, our definitions change, so it notices that, and we must recalculate our model. So if I click on OK, and yes, I want to start the calculation, we'll see a difference in the axial forces of our members. And that's exactly what we want. Here we see wind acting in the negative y direction, so from left to right across the screen. And we see only tension, and this member has been deactivated. And if we, sorry, not that direction, we see the results for that load case. We see the opposite. As I mentioned, there are many different ways that we can define this. So what we had was, sorry, let me select those beams, sorry, those bracing members. It is assigned to a member type beam, but there's a lot of flexibility in the use and ease of use with RFM. If I go on the drop-down menu, there are many different member types. So it actually takes a lot of this clicking nonlinearity defining work, takes it away from us, makes it obviously in a good way. So we can change the member type to tension. And then you see the nonlinearity tab is grayed out because this is a preset, this is a default for bracing. And if I click on OK and run the analysis again, it'll give us the exact same results, but there are just many ways to achieve what you want to do in RFM. So again, the axial load is the same as what we had when we had a when we had defined it with a nonlinearity for a beam member. So much to that example. Ismail, are there any comments or questions after that one?
Nope, all clear. We had a question about where the webinar will be posted, and that will be on our YouTube channel.
Yeah, together with the models defined in this webinar and the certificate as well, which should come a day or two later via mail. Thanks for that, Ismail. Right, looking at our third example, similar to what we're doing in the second example with tension members, we're looking at the reactivation of bracing members. So just once again, if I remove these elements and I try and run the model, irrespective of the nature of loading that we have, we need to have an adequately stable structure. So that includes proper support reactions defined, as well as a good structural concept. So if we have a look at, yeah, obviously we get the stiffness matrix, a singular issue, the structure is unstable. We get these types of examples from our statics lectures. So if I just undo that and I add the bracing back, we can now run this model. Again, stiffness matrix is singular, and that's because of the type of analysis settings we are now looking at. So if we are looking at a second order analysis, which is now getting the equilibrium on the deformed configuration of the structure. So if I open up these analysis settings, and reactivation is what is important to consider for this example. So what is happening is that we have defined, sorry, let me actually close this and just go back to our definition of the bracing member. We have a tension only member for our bracing. So what happens is we get this axial, compressive axial load acting on our columns. They deflect accordingly and they shorten. When they shorten, these bracing members will shorten as well, meaning that they'll also be in compression. Because they're also in compression, they will be deactivated, which means they will not be contributing to the stiffness, to the behavior of the structure. That's why we have this instability error. There's a way to change the behavior or the algorithm for the solving in the second order analysis, and that has to do with reactivation. So basically, reactivation will do the first iteration step. It won't ignore all of the members in tension. What it will actually do is it will take the tension member with the greatest compressive force, and it will remove it, and it will keep the other member. So if I then say, let's check deformation of failing members and reactivate where appropriate, and we have an exceptional handling for failures to be removed individually. So that's what I was saying, the one with the highest compression force will then be removed, but not all of them. So if I then accept these new analysis settings and I calculate all, we now have convergence for the second order analysis. Again, second order meaning equilibrium on the deformed configuration. And we see that this member that runs from bottom left to the top right is deactivated, where the other one has remained there and it is now in tension. So much to that example. The next example has got to do with non-linear supports, which is quite interesting. So let me just close this. So quite an interesting example. We learn a lot of standard support types in our lectures. We have our fixed support, our roller, our pin support. Unfortunately, in practice, it's quite often not that simple. Whatever it may be, strange requests from the architect or difficult building conditions, working on an existing site, and you may not be able to get exactly what you want in terms of support conditions, and you have to adapt your model appropriately. So that's what we're looking at doing here. Let's consider that we have this L-shaped steel structure, and the support conditions here are such that there's maybe a wall that the member butts up against, and it is resting maybe on a smooth surface. Let's say, for argument's sake, that there's little to no coefficient of friction that that smooth surface provides. So what would happen in reality is that if we apply a load from left to right, the structure will deform to the right and it'll push up against the wall. The wall is then providing a support reaction back, but if we had to pull or apply a force from right to left, it will then slide along the plane and there'll be no way for us to resist that force. Might sound a little bit complicated to try and now model that interactively, but that's where RFM has got some very nice and easy to use definitions. So we can see I've applied a load from right to left, which means that the structure should slide, and that is what is done if we don't have this flexibility in support conditions. And if I open up this nodal support, which is theoretically our behavior on site, we can see a non-linearity function for translation in the X direction. And that is failure if the applied load is in the negative X direction. And that again is a nice thing with RFM. There are so many easy to use presets that one can just pick, and one can also define things manually if one wants to. So I'm happy with that, obviously, because this model has already been created. And just to show the difference in behavior, we obviously have global deformations for the structure on the right that is deflecting, whereas the one on the left is not at all. And this type of support condition, which we saw when activating the properties, it is defined as a non-linearity. And it is exactly that, because we need to first see how the structure responds before we can apply these adapted boundary conditions. So much to that example. Ismail, any comments or further questions or something in the chat?
I'm just enjoying how perfectly clear you're making this look. Yeah, no questions so far.
Cool. Well, if you enjoyed those examples, hopefully you'll enjoy this next one. It's quite an interesting one. Consider we have a ladder that is propped up against a wall. Anyone who's had or worked on a ladder before knows that you just basically prop the ladder up against something, and you usually get someone to support it at the base for you so it doesn't slip out from underneath you. We can actually model that with appropriate support conditions. So we can see this 1 kilonewton load applied in the center of these ladder rungs, and we can define it such that the person is moving up the ladder, which is quite cool. Sorry, getting distracted by the little animation. So we basically...
That is cool, you're right.
Thank you. So what we want to see is at which point, if any, the ladder is going to slip out from underneath you, assuming a 1 kilonewton load. So yeah, not a it's a decent sized human, and we can look at our support conditions now for that. So if I double click here and open up the properties again, we have a non-linearity in the X and Y direction. It's clear, or it should be clear, that in the Z direction, we're always going to get a support reaction, which is non-linear. It's just what is applied down will be what is going up. But for the X and Y directions, we have this friction, and the friction is, in this case, or it is a non-linearity. So as soon as I select, so if I have none, then you'll see the UX tab disappear. But if I say friction, friction PZ, we then get a UX friction PZ tab. So if I look on here, there's only one input, which is friction coefficient of 0.2. Now, as we know from our, I think it was physics, first really introduction lectures in physics, that we take a coefficient of friction, we multiply that by a normal force acting perpendicular to the surface, and that's the drag that you'll get, and that's what we want to consider in this example. So we can straight off the bat say that we have a friction coefficient of 0.2. If our applied force is such that this friction, a coefficient of friction, is maximally utilized, then the ladder will slide. So if I bring up a view like that, we can see that that force is acting vertically down, but it's coming, or it's traveling down to the base through this inclined ladder, which means it's acting at an angle. And obviously our reaction forces now will be resolved into X and Z components. So basically, if we take 1 kilonewton, 1 kilonewton, it's applied centrally on the ladder. So in each, call it a beam, I'm not sure what the technical term is for a ladder, but in each side of the ladder will be 0.5 kilonewtons as a vertical reaction, just from simple statics. Now, if we take the 0.5 and we multiply that by a coefficient of friction of 0.2, the maximum resistance that coefficient of friction, that this configuration can provide, is 0.1 kilonewtons, if I'm not mistaken. So let's just remember 0.1 kilonewtons in the back of our mind. And if I now calculate this situation, we get some errors, which means that somewhere the ladder is going to slide away from underneath us. So let's have a look at where that occurs. Here you'll see the vertical reactions, and that can be activated. It is already done now, but it's under your results navigator support reactions. And here we can look at, let's just have a look at X and Z. So taking off Y. And so we have, when the person steps on the ladder in the first rung, a horizontal reaction of 0.01, so nowhere near the maximum resistance that our setup can provide. We start moving up the ladder, and it's starting to increase, 0.06, 0.08, 0.09, and then that's our 0.1, which is our limit value, and you can see the ladder now slides away. So it's quite I think it was quite a complicated example if you think about it, but with RFM6 it's quite easy to define. As you can see, for the support reactions, it was just for this complex non-linearity, it's just one box which one needs to define. So much to that example. We can now move on to...
Before we move on, Björn, I just wanted to, because you reminded me of this, as you were talking about friction and friction supports, The video I am currently working on, as I said, as Luba Software, we work on producing videos to kind of let you know what's all available in our software. The video that I personally am currently working on these days is an Instagram reel about nonlinear calculations. And for that reason, I would like to take 1 minute of your time, everyone that is following us right now. Just grab your phone next to you or on the desk, grab it real quick, open Instagram and follow Luba Software, just to make sure you get the reel that I'm working on right now as soon as it's published.
No pressure on the reel now. You have quite a large audience, Ismail. Your next upload.
It will definitely blow up the entire Instagram if everyone in this online training will follow us right now. All right, back to you, Bjorn.
Cool. Right. So our last nonlinear example before we dive into modeling together again is we're talking about now plastic analysis, or looking at the behavior of a steel member when it goes beyond the assumptions of Hooke's law. So Hooke's law is in the elastic realm, but we know for steel it has the property that we can actually utilize some strength beyond the yield strength. And if we want to look at that, we have here a wishbone type steel structure or surface predefined, and we have a line load applied to the end. If I just zoom around a little bit, you'll see fixed supports there. So we expect that the structure is going to deform to the right. We have applied a load of 503,572 kilonewton per meter, which is probably of face value quite a strange number for me to input, but we have some method to the madness, and that is that, so starting from right to left, it's basically solving for the force required in order to achieve a yield on this surface. So we're using a steel material with a yield strength of 235 MPa, or newtons per millimeter squared. Obviously, with our basic formula of stress is equal to force over area, we can calculate the required force by taking this yield stress and multiplying it by the area. So the question is, what area do we want to use? So we want to get yielding across this smaller section. So the dimension from that node, which is at 50 millimeters, to that node, which is at also 50. Sorry, we should be looking at the Z, my bad. So 5 millimeters at the Z and -5 at that Z. So the distance between those two is 10 millimeters. We've also defined a linear elastic material of 3 millimeters is the thickness of that plate. So going back to this, in order to calculate the force required, we take the 235 MPa, multiply that by 10 times 3, and we get that 7,050. We then want to distribute that over the width of our surface at this point, preferably not a concentrated point load. We'll get into that in the next portion, which is on singularities. Singularities is a bit of a no-go. Sorry, not singularities, but as well as nodal loads on a surface, on a defined surface. That's not something that we really want, so we want to avoid that. That's why we rather use a distributed load. So we take that surface and we distribute it over the width, which is 14 millimeters, and that's how we get our lovely value of 503,572 kilonewtons per meter. As I mentioned, we're starting off with a isotropic linear elastic material. So we are assuming that we are still in the elastic portion, in elastic analysis, where the material conforms to Hooke's law. So just checking some things here. Yep, that's all good. So let's calculate all. Right. So what do we see? What we usually get as default is the global deformations, which I mentioned. I'm not terribly interested in that for the meantime. I want to have a look at the stresses because we've applied a force which should backtrack to our theoretical yield stress. So under surfaces, under stresses, we have an equivalent stress formulation, which I've chosen the von Mises stress combination. That is a very typical stress combination to use. It's basically the way you're getting a single value for stress, but stress acts in the principal directions. So it's how do you combine that to have a design value? And von Mises has a formula, and that is what we're using at the moment. So maximum von Mises stress. The contour plot I clicked on the bottom here, surface results. That is automatically generated between your minimum value and your maximum value. So if you want to have a bit more control over what is happening, just first comment, we see that we get a maximum stress of 268 MPa, which is not what we expect because we were backtracking, we back calculated that it would reach yield stress across this portion, and we're getting something much higher than that. So if I double click on the contour plot and I limit it to 235 and I click OK, we get this arguably strange reaction or results on our surface plot. What we do know and what we can say off the face value is that we've now gone into the non-linear space. So we need to change our material appropriately to reflect that. And then one thing to mention on that point is that material nonlinearity is a add-on for RFM6. So if I right-click on my model and I go to base data, and on add-ons, we have this analysis add-on for nonlinear material behavior. I already have that checked, which means that when let me just deactivate results. When I open up my different material options, I have a isotropic plastic material. So plastic meaning we're now going beyond the linear assumptions. So isotropic plastic. And if I go into edit material just to look at what's happening, that material model has been chosen, and that is available to me now because I've activated that add-on for nonlinear material behavior. Again, a lot of very handy presets that I can pick from, but isotropic plastic surface, that is perfect for my example. As I mentioned, we're looking at the von Mises stress modulus of elasticity according to steel and the yield strength for our material, which is the same as in compression and tension, has been selected. So now we've changed the material model to represent our nonlinearity. Because we've changed our material, obviously the previous results don't apply anymore, which is that error that I got, or that pop-up that I just got now. So if I now go under calculate all with this non-linear material model, we see first of all that convergence diagram looked a bit different. And we now have a maximum, so sorry, let me now go on to maximum. I've not constrained the contour limits. I've said that it must tell me what the maximum and minimum stresses are in my model, and it is exactly 235. Then there's another load case that I created just after that, and that is 505. So it's beyond the yield strength, and you can see how the expected stress distribution is a bit more uniform, and that is obviously a big improvement for what we had when we had the linear elastic material model. Just a few remarks with regards to visualizing the equivalent stresses. You see it looks a bit pixelated. That has all got to do with how you want to view the results. So if I go under calculate, under results smoothing, we have different options. I think the standard is usually continuous within surface sets. So if you're looking over a very large domain, such as a slab of a large slab within a high-rise building, you might want to consider using that, where it will almost consider what is happening at neighboring surface elements and smooth it accordingly. But we're looking very detailed at a very small model. I mean, it's a 3 millimeter thick steel element, 10 millimeters width across there. So I really wanted to have a look at each individual surface result per element, which is also coming back to the mesh, how fine we have the mesh. So that's just a word to that. Another thing to have a look at is if I look at my UX displacements and I play the deflection shape, it gives a handy little animation to what is going on. And I can change that to also for at the yield strength. And that's for UX and UI. Just switch off the results for the time being. There we go. Just having a look again at the definition of our material. We have all of that, and that is the 235 MPa is what is reflected when we ran the nonlinearity, and that's what we want. Ismail, any questions at that stage?
No questions, but just one thing that I want to mention. What I personally love about RFM is are those little explanation next to each and every option you choose. If you go back to the window you just closed, it's just I think it's a privilege, and it's I don't remember which one, but it's a general thing in RFM. Each and every thing you apply to your structure, or you choose in those windows you use every once in a while in RFM, you always have this little explanation on the side that tells you briefly what's everything about that you're about to do. So this is one thing that maybe some people might take it for granted, but this is one thing that makes RFM one of the most user-friendly softwares, because we actually care about providing a little explanation to those who are not sure whether that's the correct choice to make. So yeah, just a small remark.
Yeah, I've also found that very useful when also defining different standard types. So surfaces or beams, especially if I have a quick example with a beam member. A lot of these things as well, I'm not sure if that's what you're also referring to, Ismail, but if I go and I toggle between the different members, it shows me the degrees of freedom. It shows me what axial load it's going to allow into the different member types, and that can be very helpful.
Absolutely.
Yeah. I think that those are the nonlinearity examples that I brought along. We will then, as mentioned, go into singularities. But before we go into that, I thought I'd start another quick poll. So the first question is, many answers can apply, and that is which examples would be appropriate for a non-linearity calculation. Many, as mentioned, it's not just one answer that applies, there may be more.
And while you answer this question and wait for the others to answer, I would also like you to grab your phone one more time and open YouTube this time, and follow us and subscribe to our channel. It's the one that has, when you open the YouTube channel of Gluba Software, you're gonna find an interesting video at the top. That video was published about 2 weeks ago or a week ago about what a bionic structure means, which actually means a structure that's inspired by nature. The reason why I mentioned this is because we're going to talk about singularities, and one of the advantages of following the forms of nature is avoiding singularities in some cases, which is something I explained in that structure analysis wiki video. So I encourage you to use these few seconds to open your YouTube on your phones, subscribe to our channel so that you get as much content as possible. And believe me, you're not gonna regret it, because you're gonna be able to check a lot of content, not only about RFM as a software, but also in terms of civil engineering terminologies that you might need someday throughout your career.
Very, very good video. I can also recommend it. So thanks for mentioning that as well.
Thank you, Björn.
I think everyone's had enough time. If I bring up the results, yeah, so all scenarios actually apply for a nonlinear calculation. So you can have nonlinear material behavior, geometric and nonlinear geometric response, or nonlinear deformations. Rods, we mentioned that earlier, almost right in the beginning of the different examples we had, where we had tension-only bracing members, as well as nodes and joints. Nodes, we had a look at the sliding, the friction support conditions that we have. So all of these options can actually apply in a non-linearity scenario. Singularities, as I mentioned. Jumping back to the presentation. So what are singularities? Where do they occur? And how do we maybe go about not having them in our model? A singularity is a point of discontinuity in our calculation model. We can say, if we've identified it correctly, that it doesn't have meaningful result. Just because we have an unfavorable result in our model doesn't mean that it's not meaningful. But if we've correctly identified a point of singularity, then yes, that is a result which is not meaningful. It is a model problem. Going back to what Ismail said, it's not a real occurrence. That doesn't happen in nature. It is just got to do with the way we're modeling. It's also not an error in the software. It's just the incompatibility of certain conditions. Typically, we say that a point of discontinuity is a point with infinite stresses and conversely internal forces. Mesh refinement does not improve the result. I think this is a very important point to emphasize. In our first example, we changed the mesh size. We made the mesh finer and finer, and that refinement of the mesh size then approached our expected result. And quite often the conclusion that people draw from that is that, okay, doesn't matter, I will create my mesh as fine as possible, then my results will always be correct. That's where a bit of engineering judgment comes into play. It's not always the case. If you have a singularity in your model, mesh refinement will actually make the situation worse. Typical singularity locations: openings and re-entrant corners, point loads, line loads, point loads, line supports, as well as stiffness changes, so jumps in your material thickness or in the material itself. So materials with quite strong differences in their mechanical properties, if they almost butting up to one another, then your load is transferring from one element to another. That's also considered to be a stiffness jump. Openings, re-entrants and corners, that can be avoided by smoothing your openings. Obviously, if that's what's happening in reality, you can smooth those sharp edges and corners. Stiffness changes in the material thickness, you can grade those changes if that is something that is reflected on site. The effect of point loads and point supports is something that we will now model together. We'll start off by actually creating the singularity and then discussing and showing ways to work around these singularities. So let me go back and I'll jump into RFM. As I mentioned, we can now model along. If you have two screens or if you have RFM open, feel free to model along. Yeah, so as we've done for the first example, we create a new model. I think this is now, I think I'm losing track a little bit. I think it's the 8th model. And we're going to label it singularity, and that is with actually no, I'll make it point load singularity. This is our first example, point load singularity. Again, types of model, looking at the degrees of freedom. That's not what we want for this example. If we go back to the 2D XY plate, that covers everything that I want to consider, that I find to be valid for this upcoming example. And I click OK. We're going to start with creating surfaces, very similar to what we did in the first example, so I won't waste too much time in doing that. This time we want to have a thickness of 200 millimeters. Because I've had previous examples on during this webinar, RFM actually remembers these. So these aren't random suggestions. It's actually quite clever in that it remembers these defined materials and thicknesses from previous models, which I've had open in the same session. Unfortunately, that's not what I want. I would like a material or a thickness of 200 millimeters. And the material that I want to assign to that is concrete of grade 30 or C3037. That isn't here, so I go to new material. It opens up the material library. I can either open up the material library here and look at filter by region, filter by material, search for the material, or I can very quickly just search right here. So if I type in C3037 according to the European standards, I can click on that and we have that defined. So I click on OK. So we have C3037, thickness of 200 millimeters, and that's exactly what I wanted for this example. Click on OK. Again, change my work plane to the YX and click at the origin. And I would like, let's call it 8 meters wide and 6 meters deep. And we've defined now that surface quite simply. So we want to now look at the singularity assigned with a nodal load. So let's create a node just in the center of our model. So I think that would be about there. Yep. Right click. And we assign that node with a load. So under new nodal load, I can assign 100 kilonewtons. I think that should do the trick. By default, it always opens up a self-weight load case. As mentioned, each load has to be assigned to a load case. That's how things work. But we only want to look at the effect of a concentrated load. So I'm going to deactivate the self-weight, even though this is called, actually no, it's called self-weight. So let's rename it something else. Let's call it concentrated load. Yeah. So we have concentrated load case, 100 kilonewtons in the center of the surface. So we have the surface with the material, with the thickness, we have loads, and then obviously we need to support the structure. So I can select the whole structure and I want to apply line loads. It doesn't matter that I've selected the surface as well, because it will only, if I click on assign line support, it will only apply line supports to line elements from my selection. And there it's already picked up those lines 1 to 4. Yeah, I want to do a hinge support. So there we have our hinge supports running around the entire surface. You can also change, just like the loads, you can change the visibility here with these toggles, which is quite useful, but I'm happy with the way it looks at the moment. Similarly to our first example, we want to have a look at the effect of different mesh sizes on our results. So what we did in the first example was we went to types for surfaces and we went to surface mesh refinements, and we clicked on new surface mesh refinement, and it took quite some time. Well, not really, but there's even a quicker way to do that in RFM, and that's here in these tables at the bottom. I think everyone quite enjoys using the tables, so I thought I'd show that here in the webinar. And the structure, we can go quickly to types of surfaces. We have the different types, and we want surface mesh refinements. So we want a surface mesh refinement of 2, 1, 0.5, and 0.25. Much quicker than the previous method. We want to also assign it to surfaces, and what we did previously was each time we clicked on, let's select the surface which it is applied to, but there's a quicker way of doing it. So we want, just like the previous example, we want 4 surfaces. So we select the whole first surface that we've defined. We want to create a copy. We want 3 copies. Displacement vector, let's say, I didn't know how wide this surface was, so I go from there to there. It's picked up that that's 8 meters. However, I want a 1 meter gap between these copies. So I change that displacement vector to 9. I click OK, and there we have our four surfaces. Now what we can do is, well, I know, because this is a very small model, I know that that's surface number 1, surface number 2, 3, and 4. If you want to see that graphically, we can go under numbering. It's now numbered everything, including the nodes. That's confusing me a little bit, so I switch nodes off. And now I can see the numbers of the surfaces. The loads are also in the way, so if I just switch that off, there we go, 1, 2, 3, and 4. And that's exactly the order that I want. So I'll just go 1, 2, 3, and 4. And we have the mesh settings now applied to the surfaces. If we want to see that, we can click on Generate Mesh. And we can see the mesh for the different surfaces. One thing to note is, like mentioning in the beginning, or going back to what I mentioned in the beginning, sorry, is the importance of node placement. And the mesh is, or the surface is meshed according to these nodes. You'll see that in each case, a mesh goes through that node that we created in the center. Right, so we have our surface mesh refinements applied to our 4 different surfaces. We want to also create a results section similar to what we did in the first example, so we can have a look at what the moments are like. So if I do that, create a results section, click on OK. Yeah, I think we can calculate all now. Cool. Just for future, I don't need the design situation, so I'll just delete those for now. Right. So again, default is our global deformations. I would like to have a look at our bending moments. So just on the results section, you can see that it only shows 1 value. And if I look at the settings now for results section, it's showing the global extremes. So in our global model, what is the extreme? I don't want that. I want local extremes. So for each surface. So if I toggle that, there we go. We get the results for each surface. These are looking at our displacements. As I mentioned, I want to have a look at the bending moments. So we see we have 4 identical situations, the only difference being the mesh size. And we can see we're going from a coarse mesh to a fine mesh, and we're going from bending moment of 37, and it's getting increasingly higher. And this is the thing with the singularity. If you make the mesh finer, it doesn't necessarily improve the result, or the result isn't actually valid anymore. So that's going against what we might have thought in the beginning with our first example, that okay, if I want to approach the correct solution, all I need to do is refine my mesh. Unfortunately, it's not that simple. We need to exercise a bit of engineering judgment. So what can we do in this situation? How can we improve our results? How can we avoid the singularities that we are getting in this model? one option is to transform the nodal load to a surface load, because the question we need to ask ourselves is this even possible? Can we even get a point load of 100 kilonewtons acting on an infinitesimally small area? That obviously is not reality. All load needs to act over a certain surface area. If it's a human walking, it acts over the area of your foot. If it's a car, it's over the area of the wheel, etc., etc. So let's see how we can mimic that. So we're going to keep this concentrated load, and we're going to create a new load case where we try and improve or we try to reduce the effects of the singularity. So we now call this rectangular load. There we go, rectangular load. And we click on OK. I copied the load case, which means that the loads have been copied, the nodal loads have been copied across. So if I toggle between concentrated load and nodal load, the loads are still there. So let me, now that we're in the rectangular load case, let me remove that. And we want to go under new free rectangular load. The nice thing about this is that we don't need to manually mesh our structure or model a small rectangle which represents what the size of where the loading is being applied, which sometimes one has to do depending on the ease of use of the software. But with RFM, it's very simple. We have these options. And what we want is, we already know the center of our loads, and we can, because we've got those nodes, and we can also give it a certain area over which the load acts. So hypothetically, let's say that our load acts over a rectangular area of 0.5 by 0.5. We need to keep everything the same because we're comparing between the concentrated load and now a solution for the singularity. So 0.5 times 0.5 gives us 0.25, and we want the equivalent of 100 kilonewtons. So this will need to be a 400 kilonewton per meter squared. So if we take 400, multiply that by 0.25, we come back at the 100 kilonewton squared. So we're just making sure we're comparing apples with apples in each load case. So for here, the center is node 1. It is assigned to surface number 1 as well, but RFM is clever. It knows the interconnectivity. So if I click on the drop down, it tells me that it can be applied to surface number 1. Click on apply and next. For this one, it is on that node, and it is assigned to surface 2. Apply and next. Just bear with me there. This is a bit of manual work. That's applied to surface number 3, and this one applied to surface number 4. Apply next. Good. So now we have a workaround for avoiding the singularities in our model. If I go back to just my visibility settings, I'm not wanting to see the numbering anymore. And now we can run this model. So if I calculate all, again, we're looking at deformations. So if I switch to, oh no, we're looking at moments. Yeah, it's exactly what I wanted. So concentrated load, we see a finer mesh starts to approach, we can say infinity, because there's no knowing where this will stop. So finer mesh is not helping us out. And what we've done is we've basically got the exact same load, but we've just casted that over a realistic surface area of which the load will act. And we see we have much more stable results. A finer mesh is actually resulting in a smaller bending moment, which is interesting because when looking at the concentrated load, one might get a bit of a shock and think, oh wow, there's a hidden monster in this result, and the more finer I make my mesh, the higher the result. But that might not actually be the case, because if we, through engineering judgment, make the model more realistic, we see that we actually have a refinement of the bending moment. So that is an example of load singularity using a nodal load. Just going back to this results section, if I go back to our concentrated load and say you have defined the model in this way, and you want to now interpret the results, and you maybe don't want to transform the nodal loads into an area load, one has an option for under the results diagram. We can see what we had here. So this increasing bending moment. And we have an option for smooth ranges. And we know that we're getting a bit of a peak at the area around the concentrated load. So what we can do is we can define these intervals. Sorry, let me just get an idea of where this is. So that's about 4 meters. And let's say we want to smooth it out 0.5 meters either side of these peaks. So that's at 4, that's at 12, that's at 20, and that's at 28. So if I say, wait, that was 4, so there should be 3.5 and 4.5. RFM will automatically calculate the length. The other was 12, so we make that 11.5 and 12.5. The third was 20, so it'll be 19.5 and 20.5, and the last one was at 28, I think, so it's 27.5 and 28.5. So now we define these smooth ranges, and as soon as I click apply, just watch what happens on these diagrams. So if I click apply, it basically, you can think of it as an integration. It takes that peak over that area and it gives you a bit of a smooth result, which you can see on this example of 31.67. If I hide the smooth ranges, we don't see that. Then there we get a smooth peak of 31.67, 30.06, I think that's 27 point something. So that's an alternative to transforming your nodal loads into rectangular load. You can maybe have a look a bit deeper into what the results diagram is telling you. Obviously, you can't smooth a valid result. So if it's a real high stress, you can't just ignore it. But in this case, because we have a singularity, we can, with good reason, validate or smooth it out. I think that is enough on point loads. I think we can do pretty much the same, but the inverse, and that is with a singularity associated with a nodal load, a nodal support reaction. So we run through these similar steps. We call this, just waiting for it to open, there we go. Nodal load singularity. Again, we're looking at the 2D XY plate. We click on OK. So we're going to do the same thing, and we're going to have 4 surfaces. Let's use, again, I want a 200 millimeter thick concrete section or surface, so 200 thick. We can go back to our, go to our concrete, which is C1337. Yeah, normal grade concrete from Europe. So C3037, 200 thick. Click on OK. OK again, and we're ready to draw. I like always flipping to my XY plane, and we make it, 8x4, I think. Exit the draw mode, and now we want to we have a line support at this end, which is hinged. We click on OK, and we want to have a nodal support in the middle, which might be a bit odd, but we just want to illustrate the effects of these singularities. So create the node first, and then assign it a support condition. So there we have it. We, again, because self-weight is default when opening a new model, we will deactivate self-weight. And then we will create a surface load of 10 kPa or kilonewtons per meter squared. Obviously, the surface load needs to be assigned to a surface, and we can do that there. And there we have our model. We're going to do the same thing as previously, so just selecting all elements, copying, creating a copy, 3 of them. I think displacement vector should be 9. Yep. And what we want to do again is create the different mesh sizes. So types of surfaces, surface mesh refinements, we want 2, 1, 0.5, and 0.1. That will be applied to surfaces 1, 2, 3, and 4, and everything is done. We now go to, let's create a results section again. And we click on OK. We now have a results section, and we can calculate all. Again, looking at our moments. Again, we're only seeing the global peak. So let's go under results section to look at all local extremes. And we have, similar to what we had in the previous example, we have a mesh refinement leading to almost like an exponential increase in our results. Again, this is quite clearly a singularity. So the question is, okay, we might have a surface element being supported by a column underneath. So a column is a 1D beam element. So when you model the beam, you will have a single node going into your surface. So it might be quite hard to avoid this situation, but there are tricks that we can employ or deploy to get around that. And obviously, for the finite element method, we reduce things to a single line for a beam or a planar surface for a plate, but they still have other properties which we want to consider. So let's, for this example, let's say that this isn't actually just a point nodal support, but a column that is sitting underneath our model. So what we can do is we can adjust the properties of this nodal support. And if we go under edit nodal support, we have this stiffness via fictitious column, which is quite handy. So if we go in the stiffness via fictitious column, we'll obviously get this new tab, and we'll say, yep, elastic surface conditions. There are many different options, but I quite like this one. It's really bringing a practical, real-world example as a diagram. So you can see there's a column that's supporting the nodal load, which is what Ismail was saying as well. Is this user friendliness is quite enjoyable when modeling. We have dimensions of this column head, breadth times height. We'll leave it at 0.5 by 0.5. Column height, obviously, that affects the stiffness contribution. If you have a very short stubby column, they'll be much stiffer than a very long slender column. So we'll leave that as 0.5 by 0.5, and we click on OK. Yes, our conditions have changed. And we can see a different nodal support attributes now. So if I display or generate the mesh again, we can see this 0.5 by 0.5, what we deem to be physical representation of the support conditions. And if we now, sorry, I want to switch off these design situations because that makes the model run a little bit longer. And if I say calculate all, we see now a difference. Whereas previously we had this peak of about 100 10, I think it was, hogging moment over this pin support, we now have a more realistic behavior of what will happen over the column head. So those are two examples when it comes to singularities associated in these examples with point loads and point supports. That is all that we have in terms of the modeling side of things. I think I have one more poll. There we go. Let's start the poll. So the question is, where do singularities occur? And there are multiple answers possible. I'll wait just a bit so everyone can have an opportunity to answer. All right, I'll close the poll and show the results. Yeah, so all of these options are locations where singularities can occur. Cool. I'll close that and jump back to the presentation. That is it in terms of the modeling side and the introduction to FEM. I think just a few more comments from our side. We've touched on it quite a few times. Ismail and I have both introduced ourselves. We are also both students. I remember I actually applied to be a VAC student at Bluewhale after a similar webinar to this about a year and a half ago, and Ismail was also sitting on the panel there, and also
I was in that webinar, yeah.
yeah, I was so impressed that I wanted to get involved, and
well, we are glad you're with us today, Björn. And
yeah,
we hope we'll see some of you guys probably working with us someday.
Yeah. So jumping back to what really took me, what really impressed me was just the plethora of resources available. Ismail has mentioned it quite a few times with the YouTube videos, with the website, with the knowledge base, cross-section properties, frequently asked questions, models that you can download for free. If you follow us on LinkedIn, which I recommend you do, you'll get to see a lot of posts of what models are available to download. We've mentioned YouTube videos. Definitely have a look at our YouTube channel. As a student, you have the ability to have a student license, which is really cool, so it can accompany you in your studies. I think it is best to actually maybe just jump away from the presentation and just show the website quickly. So if sorry, let me switch to English. Yeah, exactly. So it may be a bit overwhelming at first, but we have a lot of information, education. We have the knowledge platform, the e-learning. That's all of the really great videos that Ismail has made. You can really spend a good day here, support and learning. Here you can also request your licenses under. So if I just switch back to German to show you, under the firm tab, we have open positions. And the VAC student, working student, if any of you are interested, have some time, have a look around structural engineering, marketing. There are a lot of open positions. I think I even saw something with marketing, Ismail. I'm not sure if I saw that correctly.
Yeah, we have a bunch of open positions right now. You can contact us via email. You can send your application right away. It's really it would be a great opportunity for you guys, because right now we are hiring. That's, you know, where you see the sign, we are hiring. Bluewhale right now is hiring a lot of working students, a lot of engineers. So yeah, don't waste time. If you want to apply to us, just do it these days, and we'll definitely get back to you with a response.
I'm not sure if you can see YouTube now. Hopefully you can. But there's also another great channel. Ismail mentioned it. There's the bionic structures. Definitely have a look. Write some comments. Get involved.
It was the topic of my bachelor thesis, and I kind of had fun writing that thesis because the subject is really interesting when it comes to learning from nature to to implement principles that are found in biological systems. The way you implement those principles in structural design is amazing. I mean, just for instance, so you can have an idea what I'm talking about, a structure can be that's inspired by a tree structure can have a huge difference in terms of sustainability if it follows the same rules that are found in the biological system of what we call a tree. So I talk a little bit about that in that video, and I definitely invite you to check the entire thesis, for which the link is provided under that video. And not only that video, we actually talk about a lot of stuff in the Structure Analysis Wiki and in all the other playlists. If you can open the playlist window, Björn, we have, I mean, videos of very different types, the e-learning videos, the product features that I talked about, in which we explain what's new in RFM 6, because the release was, I think, a month or 2 months ago. We just released the newest version of RFM 6. A lot of things are new in it, and you can check that out under that playlist. We also have tutorials to help you get to where all of us are right now. And just to talk about that a little bit, I personally, it took me a few days or weeks to model my very own complete building using RFM right after starting to learn the software. It's really an easy to learn software. It's really user-friendly and what's the word I'm looking for, Björn? It feels intuitive. Very natural.
Yeah, natural, intuitive. Yeah.
Intuitive, exactly. Yeah, it's a very intuitive software that, whatever you look for, you're gonna find in the exact way that you would expect from a software. It's not a complicated software where you have to learn programming, for example, which is the case of a lot of other competitors. But in RFM and RSTEP, you just have to have a sense of a civil engineer, have look for what you look for, and you're gonna find it. You're definitely gonna find it in an easy way. If you don't, there's one more advantage of our website. We have a lot of FAQs. Any question that might occur to you, you would most definitely find the answer to in the FAQ section. And if not, if by some miracle you don't find the answer online, you can contact us anytime you want, either on our email or by calling us on the hotline that you see. You see the number right there. You can always write us and call us. So yeah, enjoy the fact that you are still students and you are able to get all this free content. You get the free license with all the add-ons. I mean, those add-ons cost a lot of money if you weren't a student. So yeah, like after finishing your studies, you would probably have to pay for each and every add-on. So use the opportunity to have a look at all these add-ons and the entire software for free. It's completely free. Share your models with us. Post them on LinkedIn, on Instagram, YouTube. We see what our audience does, and we encourage it by sharing everything we find. And we definitely encourage you to encourage us to make content for students and everyone that needs this piece of knowledge in a civil engineering career. So grab your phone one last time. Make sure you subscribed to our channel. Make sure you follow us on Instagram. We have 11.9 thousand followers right now on Instagram. So we might think about giving away some gifts for the 12,000 followers. So make sure you be there on that list. Follow us on LinkedIn. We're absolutely active on LinkedIn and on every social media platform. And Björn, I'll let the last word for you. Great job today, by the way. It's been great, and I hope you guys enjoyed it.
Yeah, I really hope you guys enjoyed it. As I mentioned, the whole webinar is recorded. We'll send you the models as well that were created during today's webinar. We mentioned frequently asked questions. There's also another thing that I'd like to mention, that is our knowledge base. We mentioned, for example, shear stiffness today. So just as an example, if you type in shear stiffness and search for different articles, here we have member transfer stiffness. That's not what I wanted. There we go, consideration of shear stiffness for cross-section calculation in RFM, and that's exactly what we did today as well, which is quite cool. There's a lot of support out there under support and learning as well, or is it under education? We have all of our online training recordings as well posted, so everything that you see on YouTube is linked with our website as well. So have a play around. I really enjoyed it today. I hope you guys enjoyed it too, and we look forward to linking up in the future. Cheers.
All right, see you guys.